Ever wondered why we need to linearise formulae? At A-level physics, we'll often collect data that gives a curve. Now this is nice, but it's hard to analyse. So how do we turn it into a straight line? And even, why would we want to? Now straight lines are absolute gold in science. Now this is because gradients and intercepts often relate to real physical constants we actually want. Get a straight line and suddenly we're able to measure the gravitational field strength of a planet, or maybe even the focal length of a lens. Now we're going to have a look at a bit of a worked example together, and we're going to use the pendulum as an example. Now you might recognise this formula if you've been working on the oscillations topic. Now this is showing the relationship between the time period of our pendulum swing, the length of our pendulum string, and also the gravitational field strength. Now as you can see, this is a bit of a clunky formula, and if we were to actually plot time period against length right now, what we'd get is we'd get a curve. Now again, that's lovely, but we wouldn't be able to do much else with this. So we'll have a look now at how we can linearise this formula so we get a nice straight line, and then use this to be able to estimate the gravitational field strength. Okay, so here is our formulae. Now, I always think it's very helpful when you're linearising just to start off by identifying your variables, the things that we're actually measuring in this particular experiment. So in this case, time period and the length of our string. Everything else in this experiment is either going to be a number or a constant. Now, what we're going to do, of course, is we're going to try and get this into the form of y equals mx plus c. I'm sure you saw this loads at GCSE. And actually, we can kind of see that we're sort of getting there already. The y-axis is looking like it's going to be something to do with t. There probably isn't going to be an intercept. There's no pluses or minuses over here. So chances are we're not going to have an intercept for this formulae. So obviously the big issue is we've got this square root. So our standard way of dealing with this, we're going to square every part of this formulae. So I'm going to square my t, so I get t squared. I'm going to square my 2 pi, so that's going to give me 4 pi squared. And then we're going to square this last little bit. And what that then leaves is L over G. Now, we're just going to try and tidy this up a little bit because what I can do, I'm sure you know, this is exactly the same thing. So we're just incorporating all of our quantities here. And then the final thing that I'm going to do is just tease this apart because we know that our variables are our length and our time period. So I'm just going to tease this little bit apart here. So what we're left with is 4 pi squared over g times by L. So what we now have, we've now got this in a situation where we've got our y-axis. So we're going to be plotting t squared on the y-axis, and we're going to be plotting x on length on the x-axis. And then finally, we're going to see that our gradient is going to be this 4 pi squared over g. So this is going to be our gradient. And this is what is going to allow us to work out what the gravitational field strength is. So let's have a little look as to what this would now look like graphically and what we can do with it next. All right then, so let's have a little look at what we've got. So we've realised that we can turn this form of our formula that gives us a curve into a straight line that looks a little bit like this. So we've seen if we plot t squared on the y-axis against L on the x-axis, we're going to get a nice straight line with a gradient of 4 pi squared over g. Now the graph that you can see here, this is actually real data that some of my students have collected. You can tell it's real data because we've got some scatter around that line of best fit. But when we actually calculate the gradient from this line, we get this value here of about 3.8. Now what we're going to have a look at is how we can now use that value for the gradient to actually work out what our gravitational field strength actually would be. Okay, so let's come back to our formulae. Now we've just seen already that the gradient from the graph, that real data was 3.84, and we know that our gradient from our linearising process is equal to 4 pi squared over g. So what we're going to do is we're going to say that 4 pi squared over g is equal to 3.84. And now all I have to do is rearrange to make g the subject. So this is going to give us 4 pi squared over 3.84. So let's get our calculator in here and see what we get. So 4 pi squared divided by 3.84 gives me a value of 10.3. And of course, this will be newtons per kilogram. Now we know that the true value for this is 9.81. So we're pretty good here. Again, this is real data. So we're not expecting it to be perfect, but we are expecting it to be close to the true value. As always in these videos, I like to give you guys the chance to put into practice what we've been looking at. So we're going to have a go at trying to linearise the equation for a mass oscillating on a spring. So again, very similar format to the one that we've just seen. We've got t as our time period, m is the mass on a spring, and k is the spring constant of the spring. So pause the video here, have a go, and we'll work through it together in a moment. Good luck. Okay, so let's see how that went. So here's our formulae. As always, good idea to identify our variables. Now we know that we're going to have to start off doing something with our square root. So just like before, we're going to square all parts of this formulae. So it looks a little bit like this. Now at which point we'll just bring these parts together again like before. It's all the same thing. And then we'll just tease this little bit apart here. So we end up with 4 pi squared over k times by m. So what we've now got, this is what we're going to plot on our y-axis, this is what we're going to plot on our x-axis, and this here is our gradient. And just like before, what we'll find is that we'll be able to use a graph of t squared against m, find the gradient from this, and we can use that to estimate the spring constant. Hope that went well. Okay, so I hope that's been a useful session for you all. What next? Well, we're going to move on to having a look at how do we linearise exponential functions. Now, these come up quite a lot in A-level, particularly in the year 13. So for example, you're going to see discharge of capacitors, radioactive decay. These all involve exponential functions. And we're going to have a look at how we can use natural logs to linearise these expressions and just to rearrange them in general, to be honest. The other thing we'll do is we'll have a look at how we can use logs with any formula that's got any sort of power in it. Now we could have actually used that today. And what's kind of cool about using logs for these types of linearization is that we can actually use that to estimate what the power relationship should be between two variables. Anyway, that's for the future. As always, like and subscribe, and please comment if there's anything I can help you with moving forward. See you soon.